Okay. So, we were discussing how this torque slip characteristics gets modified as you apply at least change two things. One is the supply voltage you can change. You can change means supply voltage can have a downward change only. You should not apply a voltage greater than rated voltage, and if you vary the supply voltage, you should be very quickly drawing. This is the torque slip characteristics, this is at rated voltage, and if you change the supply voltage to half, it will become V 1 by 2, and do not put S equal to 1, S equal to 0. This is torque. The T max, so supply voltage variation. Then we discussed about what happens if this rotor resistance varies. If rotor resistance is varied, how the torque slip characteristics changes. So, suppose this is the torque slip characteristics with inherent rotor resistance R 2, that will come as R 2 dashed with a constant multiplied. This is S equal to 1, this is S equal to 0. Now, if you increase this R 2 by connecting some external resistance R 2 external per phase, then we have seen that T max remains same, it does not change, but the slip at which maximum torque occurs, that changes. So, a number of curve can be drawn, and the slip at which maximum torque changes, that increases, and but the question is how much R 2 external should we connect? It depends upon the situation. If you are too greedy, you say that I want to get the T max to appear at S equal to 1. Yes, you can do that, because all the equations are with me. I will make then, for example, look at this equation, that torque equation in general, where you can play with these numbers. Expression of the torque is after all this one, this one. So, T max can be calculated assuming only R 2 is present, and then if you want to get at starting that T max. So, I will write T max here, put S equal to 1, this will become unknown, then R 2 dash plus R 2 external, and from this equation I will be able to predict the value of R 2 external. That is there, that equation should be used, R 2 dash equal to alpha, and what I am telling is, suppose I want to make T max remain same, T max to appear at certain value of alpha, then you can put that alpha to be equal to 1, and from this expression you will be able to calculate its numerator. If you put R 2 dashed, here something was wrong, R 2 dashed, here it was R 2 dashed in fact. Sorry, I made a mistake here, R 2 dashed. So, this R 2 dash should be R 2 dash plus R 2 external, and get the values of that. We will solve several problems, we will give in the tutorial also. So, these are the two important variation that people generally make with induction motor, maybe reduce the supply voltage, which is not done very much, because you then sacrifice T max to a large extent, and therefore, it reduces the capability of the motor to supply any substantial meaningful load torque. Okay. And another thing is, you can play with the rotor resistance, and you can get, these are the starting torque of different values. After telling up to this point, I have decided that it is better now to talk about the types of induction motor. So, remember one thing is important, that rotor resistance should not be kept permanently connected. That is, you connect R2 external, exploit that you can get higher starting torque. Depending on that, you select R2 external, connect it, no doubt. This is stator. Let us draw it. What I was telling, you connect that R external, okay, here, short it, some are external, but as the machine picks up speed, finally, that is why I showed it variable, bring it down to 0. So, that finally machine will operate at R2 with inherent rotor resistance, because if you keep this rotor resistance in the circuit, there will be additional copper losses, and that copper losses additional means efficiency of the motor will be reduced, and machine will be running at a much lower RPM, because if this is the load torque, suppose this is the load torque, if you keep this resistance, it will run at this higher value of slip and things like that. That is why motor maximum value of this alpha with its own R2 inherent resistance is about 0.1. This number is decided based on that. If suppose somebody designs a machines whose inherent rotor resistance is such that it is like this, the T max occurs with its inherent rotor resistance is such like this, then we are talking about an induction motor whose rotor resistance per phase is higher, and therefore, such machines will be not that efficient. Therefore, people try to see R2 when it will be operating, it should be low, so that rotor copper loss is reduced to a great extent, and that is why you select this value of alpha, which depends upon inherent rotor resistance. It should be like this, and full load torque, whatever it is, point of intersection will decide this speed, and which I know will be close to synchronous speed. Now, in this case, so suppose this is R2 R external, you have connected and you wanted this much of starting torque, which is greater than this, machine will accelerate. How the operating point will shift? Okay, it will shift like this, but as it shifts, what you do? You cut out this resistance. So, if you have cut out this resistance here, then it will travel to this, it will go like this. Suppose I reduce the resistance a bit, that R2 external, which is variable, then it will follow some torque slip characteristics, which is decided by R2 plus R2 external now. Then once again, suppose you cut out the resistance further, R2 external make it 0, it will move like this and it will settle down finally here. I think you have got the point. That is, you should always think that this external resistance is to be cut out, and how the operating point will move. You come here, you vary the decrease this resistance, suppose and some torque slip characteristics based on all the R2 external exist. So, it will switch over to the new torque slip characteristics, it will move there till you further reduce this R2 external, and finally, machine will be operating on this torque slip characteristics, where R2 is the inherent rotor resistance, which has been optimally designed. So, that the copper loss is reduced and you have desired efficiency level of the motor. So, this is how it is to be done. Now, what I will tell is types of induction motor. Okay? Now, this is it is at this stage I am introducing it, so that you can understand types of 3-phase induction motor. There are actually two types. One is called wound rotor induction motor, wound rotor, or this is also known by this name, slip ring induction motor, slip ring type, wound rotor or slip ring type. And another is what is called the cage type rotor. It is based on the rotor. These induction motors are classified into two groups. One is called wound rotor type and slip ring type. Some changes in the rotor only. Stator of course houses a balanced 3-phase winding in both the cases, but it is in the rotor something we are doing. There is difference between these two kinds in the so far as the rotor is concerned. Okay. Now, first in fact, so far we are discussing is slip ring induction motor, although the name I have not told, because what I have assumed is that is the stator is like this. These are the stator where there are windings. I am sorry, I always make a this is the stator, these are the windings. Okay. This is the slots. These are the teeth and here are the slots. This is the stator winding. Similarly, in the rotor you have slots here. I am showing the air gap a larger, which is not the case. This is the air gap, and there is also a similar 3-phase balanced winding on the rotor. So, both stator and rotor in this machine, both stator and rotor houses balanced 3-phase winding, both of them. It is, and that is why I was drawing like this. This is the stator winding, suppose they are connected in star. Rotor windings also a balanced 3-phase winding. This is how, this is the rotor. And we also learned that these terminals can be shorted, then the motor is said to be running with its own internal inherent R2, but it may be necessary sometimes if you want to start the induction motor against full load torque from the word go, that is S equal to 1, then it will be necessary to connect some external resistance in the rotor circuit. So, these terminals are available to you and you connect some resistance to improve the starting torque and then short it. Rotor should be closed, otherwise how rotor field will be produced. So, they can be closed either directly short circuiting or you connect some external resistance of equal values in each of the phases. So, that can be also done, we have seen. Now, the question is this rotor structure where from 3 terminals will come out from the rotor winding. As the rotor will be moving, these 3 terminals will be also moving. Therefore, these terminals, when it was stationary, if you connect the resistances just like that, these terminals which I know that will be also moving, and suppose somebody connects some stationary resistance here on the ground with these 3 terminals like this, then as the machine will rotate, these resistances too will start moving and creating chaos, is not. Therefore, to access the rotor terminals properly, it cannot be like this, that rotor terminals are there and I will connect resistance. There must be some intermediary things which will make these 3 terminals which will be rotating to appear stationary to the user of the motor, so that he can connect comfortably the resistance. Okay. So, how this can be done? It can be done very nicely like this. Suppose this is the rotor and this structure will rotate. So, also this these terminals will rotate, we know. This is suppose a sketchy diagram, but you can get the feeling. Suppose this is the shaft of the motor, shaft of the motor. Idea is important. Now, what I will do, I suppose this is R, this is Y, this is B, whatever it is, rotor terminals. What I will do, I will take 3 copper rings, okay? Copper rings, continuous copper ring, and what I will do, I will insert those 3 rings on this shaft. Shaft is metal, copper ring is metal. Of course, there will be some insulation between the shaft and the copper, it is understood, otherwise how. So, this is suppose 1 copper ring like this, I will push it, this one push it here, the second one you push it there, and the third one you push it there, and these rings are continuous ring, that is any point here electrically means all the points here, because it is copper. That is whatever voltage source, voltage point you connect, this one wire you connect it here, voltage will remain same. Anyway, so this is the, and of course, this ring should be, there should be some insulation here, some insulation, and then this is insulation. Then push it, each ring you push it. Now, you do a little bit of wiring. Wiring means this R phase, Y phase and B phase, they will be moving, no, as the rotor moves. What you do? You take a wire and once again all along the track you take this wire and terminate it, this R terminate it to this copper strip. You either screw it or weld it, whatever some convenient way. So, that this copper strip, this copper ring, this ring, no matter where the rotor is, this copper ring itself is the R terminal. Similarly, you take another piece of wire from this fellow and run it along the shaft. Now, soon you get obstructed by this first ring, make a hole in that ring and push that wire insulated, I mean you have got the idea, and you terminate it to the second one. You got the idea? This one, I mean like this I will show. Similarly, this Y terminal, but this wiring is to be done along the shaft. How can you do it? and put holes here, bring it here, that I am not showing, and it goes there. Now, as the rotor will rotate, and since these rings are on the shaft, these rings too will rotate. Does it solve my problem? Not really yet. You have to do another extra thing. What you do is this: now you connect some brushes, which I am showing it with blue stationary brush. These are stationary brush. This blue one, carbon brush you connect. With a spring holder arrangement, you push it on these rings. As the rotor will rotate, as I told you, this copper ring too will rotate. But let it rotate. I will touch something is rotating. I am putting a brush over here. That is what I am telling, which is fixed. So, no matter where this copper ring is right now, this brush will make contact with every bit of copper ring as it moves. This is stationary, mind you, stationary. So, and then the terminals of rotor is brought out from the stationary terminal, that we marked as R, if it is this R. So, this is R. So, these brushes are stationary, okay, stationary brush for R. This is B of the rotor, and this is YR of the rotor. What I am telling, these three terminals are stationary because brush is stationary. Brush is just kept over this copper ring with not so much of tightness, but it is the contact point is not very loose, but at the same time it does not obstruct the rotation of this rotor in any case. Therefore, it should be with a spring arrangement, you make a good contact with the copper ring, which will rotate, but this fellow is stationary, you can access a point. That is why this machine is called a slip ring type induction machine. There will be 3 slip rings and of course, 3 brushes, stationary brushes, which are not moving, they will touch. Therefore, no matter where your R phase is as it is moving, this fixed brush here will always indicate R phase. This fixed brush will always indicate B phase and C phase. So, this is called a slip ring induction motor, and it is then shown like this. I mean, this is the stator and rotor has got a 3 phase winding like this. In some books you will find they will show the connection like this, 3 slip rings, they are terminated this points here, and there are fixed brushes which are indicated by this, not switch, these are just indicative of the things. So, these are slip rings which will be moving along with the rotor, but it always touches this point no matter where it is. So, depending upon this RYB, these terminals are, and it is these terminals which are available rotor terminals. Understood. So, rotor windings are just like stator 3 phase balanced winding, maybe with different number of turns, that is different issue, but it is and its terminals are available through slip ring and brush. And then when the question of coming external resistance connection comes in, connect it, because we have learned, this is one of the very nice point about slip ring induction motor is that you can vary the starting torque, and even you can create that T max which the motor is capable of developing at some slip otherwise, to appear that T max at s equal to 1 by appropriately connecting these are to external. So, this is the slip ring induction motor, stator and rotor, R, Y, B, whatever way you call it, R, Y, B terminals. Okay. This is the slip ring type induction motor. Now, this rotor terminals, to one can have, if one says that okay, each phase of these windings has got two terminals. In very some special machines, these three, that is two terminals. Suppose you say that I want to get access to both R 1 R 2, I mean separately Y 1 Y 2 and B 1 and B 2, all the 6 terminals, suppose I want to have access to it. Then what is the problem? Problem is then you have to use 6 slip rings and 6 brushes. So, it is really not done like that, as you will never see a 3-phase induction motor with 6 terminals coming out from the rotor for R 1 R 2, Y 1 Y 2 and B 1 B 2, because then your length of the machine, shaft length will increase, because 6 slip rings, 6 brushes. While slip ring and brush arrangement is a very nice one, but this is also one of the things maintenance people won't like, because this brush is to be replaced for regular maintenance. Brush will wear out because of this friction between this copper ring and the brush. So, maintenance problem, I mean you have to regularly maintain the 3-phase induction motor which is slip ring type, otherwise performance of the machine will not be there. Okay. So, this is called slip ring induction motor. What is the other kind of induction motor? Is the cage induction motor. Cage induction motor, I will just tell this much. In a cage induction motor, in the rotor, you do not make a 3-phase balanced winding the way we do it for the stator. Okay. What will be there? It will be represented like this. There will be conductors in slots, and these conductors will be shorted, and we will continue with this in the next class. That is also very important. Thank you.